15th of January 1874, Central City District, Colorado Mountains. On mid-January climate tables for Colorado's mining belt, the numbers are routine but severe. Monthly means near or below 32 degrees Celsius, and at higher camps, long runs of nights below 0 degree Celsius. Yet U.S. Geological Survey and geothermal measurements from the late 19th and 20th centuries show that just a few meters under those frozen townsites, rock and soil temperatures sit near the local mean annual air temperature, often between 40 and 55 degrees Celsius, and barely move from day to night. Homesteading surveys from Nebraska and Oklahoma record that dugout houses, cut into banks and roofed with earth, were warm in winter and cool in summer, while surface cabins on the same plains could swing from 40 degrees Celsius to over 100 degrees Celsius between seasons. A later frontier anecdote claims that a Colorado miner's stupidly deep dugout stayed around 65 degrees Celsius through an 1870s winter without burning any wood. This documentary tests claims with mining camp records, dugout archaeology, USGS temperature data, and modern cave-dwelling measurements, asking a narrow question: how warm can a correctly built dugout in Colorado actually run, and how much wood can it save compared with a standard log cabin? 10th of January 1870, Colorado Mineral Belt, Central City to Leadville Corridor. A late 19th century teaching sheet on Colorado miners' daily life shows tents scattered on a hillside, and, for winter, rows of small log or frame cabins. A caption notes, "The miners built log or frame cabins to live in during the winter. The environmental baseline was unforgiving." Colorado climatology reports for typical mining elevations document monthly mean temperatures near freezing throughout the winter months. At higher camps, nightly lows below 0 degree Celsius were frequent. Recorded extremes ran far lower. Frost depths were sufficient to freeze shallow waterlines and root cellars. Snow cover summaries show weeks or months with persistent snowpack at higher towns. Weather station data from Central City, established in the 1860s, recorded January mean temperatures of 28 degrees, with recorded minimums reaching 25 degrees. At Leadville, elevation 10,152 feet, conditions were more severe. Monthly means in winter hovered near 18 degrees. Night temperatures regularly dropped below 10 degrees Celsius, with extreme readings approaching 40 degrees Celsius. Wind chill was not measured, but would have been significant on exposed ridges and in gulches where camps clustered. The standard housing that developed under these conditions followed predictable patterns. Mining camp and homesteading sources specify 1 or 2 room cabins with footprints around 12-14 to 16-20 feet. They were built of round or hewn logs. Wall thickness was effectively a single log diameter plus chinking, often moss, mud, or scrap material stuffed into gaps. For spruce or pine logs common in Colorado elevations, diameter typically ranged from 8 to 12 inches. Roofs were built with poles and boards, sometimes covered with earth, often just shingles. Small iron stoves, operating at limited efficiency, served as the main heat source. Modern reconstructions and simple heat loss calculations allow us to estimate the thermal performance of these cabins. Approximate wall R values were low. A single 10-inch log with minimal chinking provided roughly R8 to R10 thermal resistance. Modern building standards call for R20 or higher in cold climates. Typical infiltration through gaps was high. Air changes per hour in poorly chinked cabins could reach 2 to 4, meaning the entire interior air volume was replaced every 15 to 30 minutes. The stove output needed to maintain interior temperatures above 32 to 40 degrees Celsius during cold nights was substantial. Several memoirs and educational summaries describe cabins that were warm only close to the stove, cold and smoky elsewhere, with frost forming inside on the logs when fires burned low. A miner's diary from the Georgetown district noted, "Woke to ice in the water bucket, though the stove had coals. Frost thick on the logs near my bunk." The fuel consumption was documented in various accounts. A typical mining cabin in sustained cold requires 30 to 50 pounds of firewood per day to maintain minimally habitable conditions. This translated to roughly 15 to 25 kilograms. At higher elevations with extreme cold, consumption could double. The wood had to be cut, hauled, split, and stacked, labor that competed directly with mining work. Against this standard, the frontier dugout existed as a known alternative. Oklahoma and Great Plains references describe dugouts as warm in winter and cool in summer. Yet in Colorado, mining narratives, earth shelters seldom appear as the default choice. The preference for above-ground cabins persisted despite their thermal inefficiency. A typical winter day presented a clear accounting problem. A cabin might consume tens of kilograms of firewood just to hold the interior near the low 40s degrees overnight. In other parts of the West, dugouts were reported as comfortable with far less fuel. The question remained, why were documented warm in winter earth shelters not standard in these cold mining camps? 1st March 1870, Great Plains, North China, Loess Plateau, comparative sites. A homesteading bulletin from Nebraska prints a simple dugout diagram, a rectangular pit cut into a bank, roofed with poles, brush, and sod. A marginal note describes the interior as warm in winter and relatively cool in summer. The Great Plains dugout, as described in Nebraska and Oklahoma historical summaries, followed consistent construction patterns. Typical excavations ran 1-2 meters deep into a hillside or flat ground. The excavation process involved selecting a suitable bank, preferably south-facing, and cutting a rectangular chamber into the slope. Walls were exposed soil, sometimes faced with boards. Roofs were made from poles or timbers topped with brush and 30-60 centimeters of earth. South-facing doors with minimal window openings completed the structure. Dimensions varied but followed practical constraints. Floor areas of 10 to 20 square meters accommodated families of 4 to 8 people. A typical dugout might measure 3 by 5 meters internally, with a ceiling height of 1.8 to 2.2 meters. The entrance was often recessed or baffled to reduce direct wind penetration. Interior furnishings were minimal: bunks along walls, a small stove for cooking, shelves cut into the earth walls, and a table. Contemporary accounts consistently highlighted thermal comfort relative to surface cabins, even while complaining about dampness, darkness, and vermin. A Nebraska homesteader wrote in 1873, "Our dugout, though dark and close, remained tolerable through winter, while neighbors in frame houses burned wood continuously and still suffered from cold." The lens widened to global earth-sheltered dwellings. On the North China Loess Plateau, Yaodong cave houses had been monitored in modern studies. Those measurements showed winter indoor temperatures significantly higher than outdoor air, with small daily swings. Research published in energy journals documented Yaodong interiors at 50-62 degrees, when outdoor temperatures ranged from 15 to 35 degrees. Thick, loose walls and the surrounding earth mass damped external temperature changes. Typical Yaodong designs featured depths into the slope of several meters, arched roofs, and carefully sized south-facing openings. The construction method involved excavating horizontally into Loess cliffs, creating barrel-vaulted chambers. The loose material, a wind-deposited silt, was cohesive enough to stand without structural support when properly excavated. Chamber depths into the hillside reached 8 to 12 meters. The face of each chamber featured a facade with a door and typically one window, both sized to balance daylight with thermal retention. Similar earth-sheltered traditions existed in diverse climates. In Cappadocia, Turkey, volcanic tuff caves provided stable temperatures year-round. In southern Spain, cave houses in Andalusia maintained comfortable interiors through hot summers and cool winters. In Iceland, turf houses with thick sod roofs and partial earth berming achieved remarkable thermal performance in a harsh climate. Each tradition demonstrated the same principle: Sufficient earth mass surrounding living space stabilized interior temperatures near the mean annual air temperature of the region. The link to shallow ground temperature physics provided the mechanism. Geothermal and energy efficiency documents explain that at about a 1.5, 3 meters below ground level, soil temperature stabilizes near the mean annual air temperature, varying only slightly over the seasons. In climates with mean annual temperatures of 40 to 70 degrees, this means the Earth at dugout depth naturally sits in that range, while air above oscillates widely. The physics is straightforward. Solar radiation heats the surface in summer, creating a thermal wave that penetrates downward. The soil's thermal mass and conductivity determine how deep and how fast this wave travels. At shallow depths, the wave is damped, its amplitude decreases with depth, and its phase shifts in time. By 2 to 3 meters depth, the summer heat wave arrives months late and greatly reduced. Winter cold similarly penetrates but is damped. The result is a stable temperature zone tied to the annual average, not to daily or weekly extremes. Two archival elements anchored the narrative. A Great Plains account explicitly stated that a dugout stayed warm in winter. The earth house on Beaver Creek, occupied by the Johnson family, required no heating fuel save for cooking throughout the winter of 1868-69, according to county records. A thermal study line from a Yaodong paper noted, mean winter indoor temperature in unheated Yaodong dwellings measured 54.7 degrees Celsius, while mean outdoor temperature was 28.3 degrees Celsius, representing a 26.4 degree Kelvin differential without active heating. The causal link became explicit. Depth, surrounding mass, and south-facing geometry were measurable design choices that produced stable, elevated interior temperatures. For Colorado mining camps, a question arose: if homesteaders and Yaodong builders achieved winter comfort using earth and geometry, could a stupidly deep miner's dugout in Colorado be engineered to do the same without fuel? 5. November 1872. Rocky Mountain Mining Regions. American West Overview. A site plan and photograph from Mini Gulch in San Juan County, Colorado, shows a small mining camp, several timber cabins along the slope, and one marked dugout cut into the bank, identified in archaeological reports as part of a hard rock mining complex from the early 1900s. Residential patterns at western mining sites showed a mix of shelters. Archaeological and historical reports documented tents, rough shacks, more permanent log cabins, and, less commonly, dugouts or semi-subterranean structures. Sites like Mini Gulch documented this mix explicitly, with at least one dugout interpreted as a residential or storage structure alongside cabins. The archaeological record from Colorado mining sites provided additional examples. At the Cashier mine site near Silverton, excavations revealed a partially subterranean structure with stone-lined walls and a timber roof, dated to the 1880s. At the Tomboy mine above Telluride, historical photographs from the 1890s show several structures built partially into the steep slope, with earth-covered roofs. These represented adaptations to extreme conditions at elevations above 11,000 feet, where winter winds and avalanche risk made conventional construction challenging. The documented presence of Chinese miners in the broader West added another dimension. Immigration and labor studies for California, Montana, and Wyoming showed significant Chinese mining populations in the 19th century. In California's Sierra Nevada, Chinese miners comprised up to 25% of the mining workforce by the 1860s. In Montana's Alder Gulch, Chinese populations in some camps exceeded 1,000 individuals. Records suggested more limited numbers in Colorado, but confirmed their presence in regional camps. Census data and newspaper accounts documented Chinese miners in Clear Creek County, Summit County, and the San Juan region. Many of these migrants originated from regions in China where cave-like or earth-sheltered dwellings, including Yaodong, were normal. The provinces of Shaanxi, Shanxi, Gansu, and Henan had extensive Yaodong traditions dating back centuries. This implied that practical knowledge of earth housing existed within the mining labor force, even if not widely adopted by the broader population. Historical photographs from Chinese mining camps occasionally showed distinctive architectural features. At some placer mining sites, structures built partially into banks, with characteristic arched openings, suggest Yaodong-influenced construction. However, documentation is limited, and most Chinese miners in the American West lived in conventional frame or log structures, adapting to local building norms rather than importing traditional forms. Attitudes toward dugouts in American frontier writing revealed a cultural tension. Oklahoma and Plains sources described dugouts as expedient, cheap, and thermally effective. They also labeled them dark and dirty, comparing them to animal burrows. Dugouts were associated with poverty and temporary hardship, while surface-framed houses and cabins signaled success and permanence. One reminiscence noted, "The dugout kept us warm, but we lived like badgers, and resolved to build properly as soon as possible." Another source stated, "A properly made dugout house is comfortable in all seasons, though lacking in light and subject to dampness if not well drained." The cultural hierarchy was explicit in homesteading narratives. First-year settlers lived in dugouts. Second-year settlers built frame houses. The transition was described as advancement, regardless of thermal performance. A Kansas homesteading guide from 1879 advised, "The dugout serves for the first season, providing adequate shelter at minimal expense. But a framed dwelling should be erected as soon as circumstances permit." This stigma operated even when dugouts demonstrably outperformed surface structures. The social signaling value of an above-ground dwelling outweighed the practical advantages of earth shelter. In mining camps, where populations were transient and status was tied to strike success rather than domestic arrangements, the stigma may have been less pronounced, but it still influenced choices. The paradox stood clear. Miners operating in a harsh winter climate had access to both the physical conditions and at least some cultural knowledge necessary to build thermally superior earth shelters. Yet the prestige of above-ground cabins and the stigma of living underground kept dugouts marginal. That set up the analytical test of the stupidly deep dugout claim. 5 February 1925-1980, Western U.S., USGS Geothermal Surveys and Ground Temperature Studies. A table in a USGS bulletin lists temperatures measured at various depths in boreholes across western states. At 2 to 3 meters, values cluster in the 40-60 degree Celsius range, while deeper points slowly trend hotter. Geothermal data translated into practical dugout limits. Reports from USGS and national standards documents described how, at shallow depths, seasonal temperature swings were heavily damped. At roughly 1.5 to 3 meters below the surface, temperatures decoupled from daily extremes and stabilized near the mean annual air temperature. NIST and related technical reports provided numeric examples from several stations. A USGS study from the 1960s documented soil temperatures at various depths in Fort Collins, Colorado. At 10 centimeters depth, annual temperature range was 70 degrees Celsius, from summer highs near 80 degrees Celsius to winter lows near 10 degrees Celsius. At 1 meter depth, the range compressed to 35 degrees Celsius, with summer peaks near 60 degrees Celsius and winter lows near 25 degrees Celsius. At 2 meters depth, the range was only 15 degrees, oscillating between 48 degrees Celsius and 33 degrees Celsius. At 3 meters, the temperature remained nearly constant at 42 degrees Celsius year-round, matching closely with the site's mean annual air temperature of 43 degrees Celsius. Using Colorado climatology for high-elevation settlements, mean annual air temperatures for mining towns fell in the mid-40s to low 50s range. Central City, at 8,500 feet elevation, had a mean annual air temperature near 41 degrees. Leadville, at 10,152 feet, averaged 3070. Georgetown, at 8,530 feet, averaged 39 degrees crushed. Breckenridge, at 9,600 feet, averaged 35 degrees. Under the ground temperature rule, soil and rock at dugout depth in these districts would rest in roughly the same band, typically 35 to 45 degrees, depending on elevation. Shallow earth conditions contrasted sharply with deeper mine environments. Mine temperature data showed pronounced geothermal gradients at depth. Typical gradients ranged from 15 to 30 degrees per kilometer of depth, or roughly 1 degree per 100-200 feet. But a miner's dugout was unlikely to reach hundreds of meters below the surface. It operated in the shallow zone, where the practical cap was the local annual mean, not the much higher temperatures of deep shafts. Deep mine temperatures were well documented. At the Homesteading mine in South Dakota, temperatures at 1,000 feet depth reached 70 degrees. At 2,000 feet, they exceeded 85 degrees. At 4,000 feet, they approached 100 degrees. These elevated temperatures came from geothermal gradients, not from shallow seasonal effects. For a shallow dugout at 3 meters depth, the geothermal contribution was negligible, less than 0.1 degrees above the mean annual surface temperature. Cabin behavior provided the comparison. Above-ground cabins, with light walls and high infiltration, tracked outdoor air more closely. They oscillated with diurnal cycles and required continuous stove input to maintain minimum comfort. A thermal analysis of a typical log cabin showed that without active heating, interior temperature would quickly equilibrate with outdoor air, lagging by only 2 to 4 hours, due to the limited thermal mass of logs and furnishings. An archival fragment from a ground temperature study emphasized the stability of subsurface temperature across daily and even weekly periods. At a depth of 2 meters, the soil temperature at this station varied less than 3 degrees over the course of a month, while surface air temperature ranged across 45 degrees. The first quantitative boundary emerged in a high-elevation Colorado setting with a 45 to 50 degree House mean annual air temperature. Basic physics made a continuously unheated 65 degree House dugout unlikely, but a stable 45-55 degree House interior with minimal variation was not only plausible but expected if the dugout was deep and well sealed. 20th December 1878. Great Plains and Western Dugout Regions, Nebraska, Oklahoma, Kansas. A Nebraska State Historical Society page labeled Dugout Construction shows a rectangular ground plan, a profile of a pit 1.52 meters deep, and notes on roof poles, brush, and sod thickness. A technical profile of 19th century dugouts assembled from Nebraska and Oklahoma documentation showed consistent patterns. Typical floor areas ranged from about 10 to 20 square meters. A family dugout might measure 3 by 5 meters internally, providing 15 square meters of floor space. Depths were commonly 1 to 2 meters below surrounding grade. Walls were left as packed earth or lined with boards. Roofs were built of poles spanning the width, overlaid with brush or planks, then topped with 30-60 centimeters of earth. The construction sequence was documented in homesteading guides. First, a suitable bank was selected, preferably facing south or southeast for solar access. The excavation began by cutting a vertical face, then digging horizontally into the slope. Earth was removed with picks and shovels. The floor was leveled, and sometimes covered with planks. Walls were smoothed, and if soil was unstable, faced with vertical boards or stones. The roof structure was critical. Poles or small logs, typically 4 to 6 inches in diameter, were laid across the width of the dugout, spaced 12 to 18 inches apart. Brush, small branches or planks covered the poles, preventing soil from sifting through. Finally, 30-60 centimeters of soil was mounded over the roof, sloped gently outward for drainage. The total roof loading was substantial. Earth at roughly 100 pounds per cubic foot meant that 50 centimeters of soil added 300-400 pounds per square meter, requiring sturdy support. Multiple independent accounts from these regions described dugouts as warmer than surface cabins in winter and cooler in summer. Problems with dampness insects, and limited light were noted. These descriptive statements functioned as qualitative thermal observations, consistent across diverse locations. A homesteader's letter from Kansas, dated February 1879, provided specific detail. Our dugout, though cramped and dark, remains remarkably warm. On a morning when the mercury stood at 8 degrees outside, the interior measured 48 degrees without fire, save the cook stove used briefly for breakfast. Modern reconstructions and studies of earth-sheltered housing moved the analysis from description to measurement. Building science literature showed that when a room was surrounded by earth of adequate thickness, the effective U values were low, and interior temperature swings were small, especially when internal gains from occupants and cooking were present. The U value, or overall heat transfer coefficient, measured how readily heat passed through a building envelope. A lower U value indicated better insulation. Typical earth walls at 1 meter thickness had U values around 0.3 to 0.5 Wm2K, comparable to or better than well-insulated modern walls. The Earth's thermal mass further stabilized temperatures by absorbing and releasing heat slowly. Simple heat loss equations estimated how much wood a log cabin would require to achieve an interior temperature matching that of a dugout in the same climate. The calculation involved a surface area, U values, temperature differential, and duration. For a cabin with 100 square meters of exposed surface area, average U value of 1.5 Wm2K, maintaining a 20-degree Earth temperature differential, say 40-degree hour showers inside when 20-degree hour showers outside, required continuous heat input of roughly 3,000 watts, or about 10,000 BTU per hour. Over 24 hours, this totaled 240,000 BTU, equivalent to roughly 30 to 40 pounds of dry wood, burned at typical stove efficiency. With the dugout's walls tied to ground temperature, only roof and entrance losses mattered significantly. If the roof had similar U value to walls due to thick earth cover, and the entrance was small and baffled, total heat loss was drastically reduced. The dugout's interior temperature would naturally hover near the surrounding earth temperature, with modest elevation due to occupant metabolic heat and cooking. A representative line from a plains source provided the benchmark. Our dugout on Deer Creek remained comfortable through the winter of 1867 to 68, though we burned scarcely any wood save for cooking. The numeric comparison clarified the advantage. Given identical climates, calculations suggested that a properly built dugout could reduce heating demand by well over half compared with a similarly sized log cabin. The thickness of earth above and around the room linked directly to measurable wood savings. 15th January 1905, Western U.S. Mines, Global Mine Temperature Studies, 1870-1930. A mine safety report reproduces a chart of underground air temperatures at various levels. Even in winter, some headings show temperatures above 80 to 90 degrees, and heat stress is listed as a concern for deep crews. Mine ventilation and occupational health data recorded temperatures in drifts, headings, and shafts at different depths and in differing rock types. Many mines showed temperatures near or above the local mean annual surface temperature at shallow levels, rising further with depth. These temperatures remained relatively stable despite surface weather. Documentation from Colorado mines provided specific examples. At the Smuggler mine near Aspen, temperatures at 500 feet depth measured 58 degrees Celsius in January when surface temperatures hovered near 0 degrees Celsius. At the Tomboy mine above Telluride, winter temperatures in the upper levels stayed near 45 degrees Celsius, while surface camps endured readings below 20 degrees Celsius. The Molly Gibson mine in Aspen recorded 65 degrees Celsius at 800 feet depth. The winter contrast was pronounced. When surface air was far below freezing, air a few tens of meters underground could be 20-30 degrees warmer. Miners' accounts sometimes mentioned the relief of stepping underground in midwinter, because it felt warm compared to the camp. A miner's diary from 1889 noted, "Went below in the morning, thermometer showing 12 the green at the shaft house. Down at the 300 level, warm enough to work in shirt sleeves. Coming up at day's end, the cold hit like a wall. Archaeological evidence suggested that in some mining landscapes, small adits or enlarged tunnels were used as storage or occasional shelter. At sites like Mini Gulch, dugouts and cabins coexisted, indicating that miners experimented with several forms of shelter, depending on terrain, labor, and access. Limits and risks constrained the practice. Mine workings introduced hazards of rockfall, water ingress, gases, and dust. Most were cut and supported for extraction, not habitation. Their suitability as housing was constrained by those conditions. Carbon monoxide from blasting, radon gas in some rock types, and the constant risk of collapse made active mine workings dangerous living spaces. However, abandoned adits or deliberately excavated residential spaces adjacent to mining operations could incorporate the thermal advantage without the active hazards. The key was sufficient depth below the surface to reach stable ground temperature, proper ventilation to maintain air quality, and structural security. A measured contrast closed the chapter. Air temperature in near-surface rock openings could easily be 20 or more above the outside winter air. That number established a physical basis for the idea that a carefully shaped, shallow underground room could offer passive warmth compared to surface cabins, provided safety and ventilation problems were solved. 10 March 2024. Analytical Reconstruction, 1870s, Colorado Climate Assumption. A cross-section sketch shows a Colorado hillside, a horizontal tunnel entrance cut into the slope, and a living chamber whose floor lies 2.5, 3 meters below original ground level, surrounded on all sides by earth. The analysis moved from historical data to transparent engineering reconstruction. At the outset, it was clear that no detailed 1870s Colorado plan survived for a stupidly deep dugout of the type implied by the anecdote. What followed was an analytical model drawing on documented dugout and Yaodong practice and measured ground temperatures. Key design parameters were defined. Floor area, roughly 3 or 4 meters, or 12 square meters. This provided adequate space for a single occupant or two in close quarters, with room for a bunk, small table, and storage. Ceiling height, about 2 meters, sufficient for standing and moving. Surrounding earth thickness, at least 1 to 1.5 meters on walls and roof, necessary to engage stable ground temperature and provide structural support. A short entrance vestibule sloped slightly upward from the living area to the outside, creating a cold air trap. This configuration leveraged the principle that cold air sinks. As cold outside air entered, it would flow down into the vestibule and remain there, forming a buffer zone. Warmer air in the main chamber would be retained. The entrance could be closed with a simple door or blanket for further isolation. A small, controllable vent or chimney was placed near the ceiling, opposite the entrance. This allowed stale air and excess moisture to escape, while minimizing heat loss. The vent could be sized at 10 to 15 centimeters diameter, sufficient for air exchange, but small enough to limit thermal losses. Using approximate U values for earth-covered walls and roofs derived from building science literature, and assuming a ground temperature of 45-50 degrees Celsius as established earlier, the steady-state interior temperature could be estimated. Earth, at 1.5 meters thickness, provided a U value near 0.3-0.4 Wm2K. The surrounding Earth was at 47 degrees Celsius, assumed mean annual air temperature for a mid-elevation Colorado site. With only one occupant and a small oil lamp as heat sources, the calculation showed how small internal gains shifted air temperature slightly above ground temperature, while the massive envelope damped losses. Human metabolic heat at rest, roughly 80-100 watts. An oil lamp, 40-60 watts. Total internal gain, 120-160 watts. Heat loss calculation. The dugout had roughly 40 square meters of wall and roof surface area. Walls, 2 meters high, 30 meters perimeter, sure 28 meters. Roof, 12 meters. with U value of 0.35 WM2K and assuming interior stabilizes at 52 degrees while ground is at 47 degrees. Temperature differential was 5 degrees, or 2.8 Celsius. Heat loss, 40 miniterm x 0.35 WM2K x 2.8 39 watts. This balanced against the 120-160 watts of internal gain, suggesting interior temperature would rise several degrees above ground temperature. The entrance and vent added losses, but if properly sized and baffled, these remained modest compared to the massive earth envelope's stabilizing effect. Throughout, specific features connected to documented descriptions. South-facing openings appeared in Nebraska dugout guidance. Thick overhead cover matched Yaodong studies. The design was not speculative, but assembled from real historical templates. The design target expressed itself numerically. In a climate with a mean annual air, temperature of roughly 45-50 degrees worse, a dugout of about 12 square meters floor area, 2 meters height, and at least 1 meter of earth cover on all sides could reasonably be expected to stabilize in the high 40s to low 50s degrees without active heating, a clear, technically grounded benchmark for partial room comfort. 5. April 2005, 2020. Cave Environment and Mine Ventilation Studies. A diagram from a Cave Environment Institute shows a nearly flat temperature line through the year, but humidity close to 100%, with arrows indicating airflow dependence on entrance height and shape. Non-thermal constraints faced any miner's dugout. Cave environment research showed that while underground temperatures were stable and close to rock temperature, humidity often approached saturation. Without ventilation, condensation and mold were inevitable. Airflow patterns depended strongly on the relative heights and areas of entrances and vents. Studies of natural caves documented relative humidity consistently above 90%, often reaching 98-100%. This occurred because the stable temperature of cave air was typically at or near the dew point of entering air. When warm, moist outside air entered a cool cave in summer, moisture condensed. In winter, the process reversed, but humidity remained high because the small volume of cave air could hold limited moisture, and any water present in the cave, seepage, condensation, maintained near saturation conditions. For habitation, sustained high humidity created problems. Clothing and bedding remained damp. Mold and mildew grew on organic materials. Condensation dripped from walls and ceilings. Respiratory problems increased. Historical accounts of dugout living frequently mentioned these issues. Mine ventilation and underground housing studies added data on CO2 and other gas buildup in enclosed spaces. They provided formulas or empirical results for how air change rates affected both air quality and heat loss. A single person at rest produced roughly 200-250 milliliters of CO2 per minute. In a 12 square meter dugout with 2 meter ceiling, 24 cubic meters volume, this would raise CO2 concentration by roughly 500 ppm per hour without ventilation. Safe indoor CO2 levels were below 1,000 ppm. Levels above 2,000 ppm caused drowsiness and impaired cognition. Increasing ventilation improved air freshness and lowered humidity, but it also brought interior temperatures closer to outside values. The challenge was finding the optimal balance. Too little ventilation created unhealthy, damp conditions. Too much ventilation eliminated the thermal advantage. The reconstructed dugout allowed several configurations to be modeled qualitatively. A large, permanently open doorway provided maximum ventilation, but eliminated thermal advantage. With no barrier to outside air, the interior would equilibrate with external conditions within hours. A modest door with no vent created stagnant, humid conditions. CO2 would build up, humidity would approach saturation, and condensation would drip continuously. A small, baffled entrance combined with a small, high vent balanced requirements. This third configuration leveraged natural convection. Warm air rose to the ceiling and exited through the vent. Cooler outside air entered through the lower entrance, but was baffled, so it didn't create drafts. The cold air trap in the vestibule further reduced direct airflow. Air change rates could be adjusted by varying vent and entrance sizes. A target of 0.3–0.5 air changes per hour provided adequate fresh air while retaining thermal performance. For each configuration, expected interior temperatures and moisture levels could be discussed. Optimal comfort required a balance between air exchange and thermal retention. A short note from a Dugout report referenced the practical challenge. The roof dripped constantly in spring, and we were obliged to cut a small chimney hole to clear the air, which reduced the warmth somewhat, but made the dwelling bearable. Depth and surrounding soil were necessary, but not sufficient. The most thermally efficient earth shelters were also stupidly careful about entrance size, vent placement, and drainage. The geometry of openings directly controlled both breathable air and the rate at which precious underground warmth was lost. Drainage considerations were equally critical. Groundwater seepage, especially in spring when snowmelt infiltrated, could flood a dugout if not properly managed. The floor needed to be above the local water table, ideally with a slight slope toward a drain channel. External drainage ditches around the dugout prevented surface water from percolating through the roof. Modeled cold wave based on historical Colorado records. A graph from a Colorado climatology report traces a 21-day sequence in midwinter. Nightly lows consistently below 0 degrees F, with several dips towards 20 degrees, and daytime highs rarely exceeding freezing. Using this documented cold wave profile, a direct comparison between two shelters could be constructed. One was the standard 1870s log cabin from earlier analysis, a 16-sec 20-foot structure with single log walls, basic chinking, and a small iron stove. The other was the reconstructed deep dugout, about 12 square meters of floor area, 2 meters high with 1.5 meters of surrounding earth, and minimal openings. The cold wave profile matched historical records from Central City in January 1880. Daily low temperatures ranged from 2 degrees Celsius to 24 degrees Celsius. Daily highs ranged from 8 degrees Celsius to 28 degrees Celsius. The mean temperature over the 21-day period was 8 degrees Celsius. Total snowfall during the period was 36 inches. Wind averaged 12 mm/hour with gusts to 35 ms. Simplified heat balance calculations simulated interior temperatures over the 21 days. For the cabin, stove output during waking hours was included, along with cooling periods overnight when fires burned low, and significant heat loss through walls, roof, and infiltration. The cabin model assumed the stove operated at 10,000 BTU-hour output for 12 hours daily, 6 a.m. to 6 p.m., with the fire banked overnight providing minimal heat. Total daily input, 120,000 BTU. The cabin's envelope losses, with 100 square meters surface area, U value of 1.5 WWM2K, and 4 air changes per hour, required substantial heat to maintain interior temperature. The simulation showed interior temperatures peaking near 55–60 degrees hours in late afternoon, dropping to 25 and 35 degrees hours by dawn. On the coldest nights, interior temperatures briefly touched freezing. For the dugout, a constant interior temperature regime dominated by ground-coupled walls, small internal gains, and low air change rates through a small entrance and vent was modeled. With ground temperature at 45 degrees Celsius and internal gains of 120–160 watts, the dugout maintained a steady 49–52 degree watt throughout the period. Daily and nightly variations were less than 3 degrees Celsius. The model yielded daily minimum and maximum interior temperatures for both shelters. Required cabin heat input converted into firewood mass per day using typical energy content values for dry wood and approximate stove efficiency. Dry pine firewood contained roughly 8,000 BTU per pound. At 40% stove efficiency, typical for small iron stoves of the period, useful heat was 3,200 BTU per pound. to deliver 120,000 BTU daily required 37.5 pounds of wood. Over 21 days, total cabin firewood consumption, 787 pounds, or roughly 360 kilograms. This required cutting approximately 0.4 cord of wood. At elevation in winter conditions, cutting and hauling 0.4 cord represented roughly 15-20 hours of hard labor. The time needed to cut and haul that wood under winter field conditions could be estimated. Historical logging productivity data suggested that one man could cut, split, and stack roughly 0.5 cord per day of hard work in summer conditions. In winter, with snow, cold, and reduced daylight, productivity dropped to perhaps 0.3 cord per day. Thus, 0.4 cord required roughly 1.5 days of dedicated effort every 3 weeks, or about 3 hours per day on average. A mining comment anchored the labor dimension. In severe cold, 2 men spend half each day gathering and hauling fuel, leaving scarce time for productive work. Over the 21-day cold wave, the dugout interior remained in roughly the 48-52 degree range, without any active heating. The cabin required substantial daily wood simply to prevent the interior from dropping below freezing. The contrast in total wood mass and work hours established, in numbers, the fuel-saving potential of deep earth shelter. The survival implications were stark. A miner in a cabin who fell ill, injured himself, or simply ran out of wood faced interior temperatures dropping to life-threatening levels within 12-24 hours. A miner in a dugout could survive extended periods without fuel, as the interior never approached freezing. On a workbench, a notebook page is headed 65 degrees dugout. Below it, columns are labeled ground temp, metabolic, lamp, and solar. The anecdote that motivated the analysis required explicit testing. A stupidly deep Colorado dugout, allegedly at 65 degrees, all winter with no fire. At the outset, it was stated that despite targeted searches, no mining camp logbook or official record had been found that documented this precise figure or identified a named individual. The story was treated as a frontier anecdote, not a verified measurement. The previous thermal model extended by adding plausible internal and solar gains. For 1 or 2 occupants, metabolic heat outputs on the order of 80-100 watts per person at rest were included, plus a few tens of watts from an oil lamp or candle. 2 people at rest, 160-200 watts. An oil lamp, 50 watts. Total internal gain, 210-250 watts. Solar gain through a small south-facing entrance was considered, particularly on clear winter days at high altitude. Colorado's high elevation and low humidity meant strong solar radiation even in winter. Clear day solar irradiance at 10,000 feet elevation in January could reach 800-1,000 watts per square meter on a south-facing surface at midday. A small entrance of 1 square meter, even with a door that could be opened during sunny daytime hours, might admit 200-400 watts of solar heat during peak hours. Over a 6-hour window of useful sunlight, this added significant heat. However, the opening had to remain small to limit heat loss during the remaining 18 hours. The combined heat gains, 210-250 watts internal plus 200-400 watts solar during peak, totaled 410-650 watts during sunny daytime periods. Compared to the dugout's steady-state heat loss of roughly 40-60 watts through the Earth envelope, small temperature differential between interior and ground, this represented a substantial surplus. The thermal mass of the dugout's interior absorbed this surplus, raising the air temperature during the day. The question was, how much? With 24 cubic meters of air, specific heat capacity 1.2 kJ m3k, and perhaps 500 kiloricre of exposed earth on walls and floor, specific heat capacity 1.0 kJ kgk, total thermal mass was modest. A 600-watt surplus operating for 6 hours delivered 13,000 kJ of heat. This could raise the interior temperature by roughly 20 degrees Fahrenheit if fully retained. In practice, heat losses through the entrance, even if baffled, and vent increased proportionally with temperature differential. As interior temperature rose above ground temperature, losses accelerated. The system would reach an equilibrium where heat gains balanced heat losses. Combining these inputs with ground temperature constraints, the estimate showed that interior air temperature could rise to roughly 55 to 62 degrees on sunny days when occupants were present and the entrance was strategically managed. On cloudy days or nights, temperature would drop back toward the baseline 48 to 52 degrees range. Results compared to measured winter indoor temperatures in Yaodong and other earth-sheltered dwellings. Field studies reported winter interiors often in the high 50s to low 60s degrees range, with modest heating or favorable solar conditions. A quantitative line from a Yaodong study provided a reference value. Winter indoor temperatures in occupied Yaodong averaged 57 to 61 degrees Fahrenheit, with peaks near 65 degrees on sunny afternoons, while outdoor temperatures ranged from 15–35 degrees. The technical verdict was clear. Under Colorado conditions, the modeling suggested that brief peaks approaching 60–65 degrees inside a deeply cut, occupied dugout might be possible, especially on sunny days. But a constant no-fire 65 degrees throughout the winter was unlikely. What was strongly supported by both physics and comparative field data was a sustained interior range in roughly the low 50s DGOEF, with much higher stability than any surface cabin. The 65 degrees claim, if it had any basis, likely represented a peak measurement on an optimal sunny day, with 2 occupants and strategic passive solar management. It did not represent a continuous state. The more conservative and well-supported conclusion was that a deep dugout could maintain 48–55 degrees Fahrenheit continuously without active heating, with occasional peaks 5–10 degrees higher under favorable conditions. 19th century Colorado. A summary table shows, for the 21-day cold wave, cabin, total wood used, minimum interior temperature, and dugout, total wood used, minimum interior temperature. Thermal and fuel results converted into survival metrics. Drawing on modern cold exposure data, air temperature and exposure duration related to hypothermia risk for a resting person. Interior cabin temperatures that sagged close to freezing during the night were associated with elevated risk if the occupant was ill, exhausted, or without adequate bedding. Dugout temperatures in the high 40s DGF and low 50s DGF fell well within safe ranges for clothed, resting occupants. Medical studies of cold exposure established clear thresholds. At 32 degree highs, a resting person in light clothing faced hypothermia risk within hours. At 40 degree hive, risk decreased, but remained present for extended exposure. At 50 degree hive, a clothed person could rest safely indefinitely. The cabin's nighttime lows of 25 to 35 degrees fire placed occupants in danger. The dugout's stable 48 to 52 degree hive provided a genuine safety margin. Workload considerations followed. Using typical productivity rates for hand woodcutting and hauling in winter conditions, the hours per day a miner would need to dedicate to fuel gathering to maintain cabin temperatures could be estimated. Earlier analysis showed roughly 3 hours daily for fuel work. In the dugout scenario, little or no fuel was needed for basic survival warmth, freeing time for ore hauling, timbering, or hauling supplies. This time advantage translated directly to economic outcomes. A miner who spent 3 hours daily on fuel gathering had 3 fewer hours for mining. At average pay rates and ore values, this represented significant lost income over a winter season. The dugout's thermal performance effectively added productive hours to each day. Risk profiles contrasted. Wood-heated cabins introduced hazards of chimney fires, accidental burns, and carbon monoxide buildup from poorly vented stoves. Earth shelters brought different risks: dampness, potential structural collapse if improperly constructed, and air quality issues if ventilation was neglected. But they eliminated the constant fire risk. Historical records documented numerous cabin fires in mining camps. Overheated stovepipes, sparks on shake roofs, and unattended stoves caused regular losses. A December 1882 newspaper from Leadville reported 3 cabins burned this week. Losses total 800. One miner severely burned. A historical comment described the exhaustion. By February, the labor of keeping warm exceeded the labor of mining, and men grew too tired to work their claims. Under the same documented cold wave, a miner in a properly designed dugout could maintain a survivable interior climate with little or no fuel. A miner in a standard cabin became critically vulnerable within hours if wood or labor supply failed. The survival margin expressed itself not as sentiment, but in degrees, hours, and kilograms of wood. The comparison extended to respiratory health. Constant wood smoke in poorly ventilated cabins caused respiratory irritation and increased infection risk. Dugouts, if properly ventilated, provided cleaner air. Historical accounts noted that despite dampness concerns, well-ventilated dugouts often had better health outcomes than smoky cabins. 1870-1950, Colorado and wider American West, a sequence of photographs. An abandoned dugout on the plains partly collapsed into its bank, the weathered cabins at Minnie Gulch, and a contemporary earth-sheltered home with a south-facing facade buried in a hillside. Despite demonstrated efficiency, earth shelters remained marginal in mining regions. Historical photographs and site descriptions showed that as soon as miners or homesteaders could afford it, they replaced dugouts with framed houses or log cabins. Local histories and reminiscences often described moving up from a dugout into a proper house as a sign of progress, while acknowledging the dugout's warmth. The commonly cited disadvantages summarized: poor light, dampness, susceptibility to flooding if drainage was inadequate, and social associations with poverty and temporary hardship. Dugouts and semi-subterranean spaces remained aligned with making do, not with success or permanence. The poor lighting was genuine. Even with a south-facing entrance, interior illumination in a deep dugout was limited. Candles and oil lamps provided minimal light. Tasks requiring good vision, reading, detailed handwork were difficult. This mattered less for miners who spent daylight hours underground at their claims. But for families, the darkness was oppressive. Dampness was manageable, but required attention. Without proper drainage and ventilation, dugouts became wet and moldy. With proper design, they remained dry, but this required knowledge and effort. Many hastily constructed dugouts suffered from moisture problems that gave the entire category a bad reputation. The measured thermal advantages and fuel savings documented earlier juxtaposed against these perceptions. In terms of degrees of warmth per unit of construction material and fuel, deep earth shelters appeared to outperform many cabins. Yet they rarely received the design attention or prestige that would have optimized them. An archival reminiscence provided illustration. Our first winter in the dugout was warm enough, though dark and close. Come spring, we built a proper cabin and felt ourselves advanced, though we burned twice the wood thereafter. In mining towns, earth shelters were seldom viewed as engineered solutions. Evidence evaluated on energy and survival metrics showed they often delivered better performance than the structures that symbolized arrival and respectability. The cultural preference for above-ground housing persisted even when it imposed real costs in fuel, labor, and survival risk. This pattern repeated across the frontier, suggesting that social signaling often outweighed practical optimization in housing choices. A modern sketchpad shows a simple section: earth cover depth, wall thickness, roof load, floor drain slope, and vent size, alongside a printed table of Colorado climate data. The historical and analytical work converted into practical design guidance. Key parameters recurred across dugouts, Yaodong dwellings, ground temperature studies, and modern earth-sheltered buildings. Depth: a minimum of 2 to 3 meters of cover above the living floor, and at least one 1.5 meters of soil around walls appeared necessary to fully engage stable ground temperatures. Shallower construction failed to decouple from surface temperature swings. Wall and roof, materials, and thicknesses must ensure low thermal conductivity and structural security under earth loads. Modern materials like reinforced concrete, pressure-treated lumber, or steel enable safer, more durable construction than historical methods. Orientation. A south-facing entrance in cold northern hemisphere climates maximized solar gain, while limiting direct exposure to prevailing winter winds. The entrance size balanced daylight, solar gain, and heat retention, typically 1 to 2 square meters of opening. Drainage and moisture control. Floors must slope gently to a drain. Roofs required adequate waterproofing layers to avoid chronic dampness. Modern membranes, French drains, and sump systems solve historical moisture problems. Ventilation. Small, controllable vents or short chimneys placed high in the space provided sufficient air exchange without excessive heat loss. This aligned both with dugout practice and with cave and mine ventilation findings. Target air change rates of 0.3–0.5 per hour balanced air quality and thermal retention. Ground temperature. Data from energy efficiency sources confirmed that in cold winter, high-elevation climates with mean annual temperatures around 45 to 50 degrees Celsius, such a design could maintain interior temperatures in the mid-40s to mid-50s degrees Celsius without active heating, with higher peaks under occupancy and sunshine. Modern earth-sheltered design added features unknown to 19th century miners. Insulated roofs with separated waterproofing and insulation layers, mechanical ventilation with heat recovery, LED lighting, and modern moisture barriers all enhanced performance, while preserving the fundamental thermal principle: deep earth coupling to stable ground temperature. Performance expectations expressed numerically. An earth-sheltered room in such a setting could provide a 40–60 degree tolerance buffer between sub-zero outside air and interior conditions. That buffer often equaled the difference between a structure that was lethal if the fire went out, and one that remained survivable without fuel. The documentary ended with a single precise metric: the shallow Earth's stable 40–55 degree of temperature band, when correctly harnessed with depth, mass, and controlled openings, could cut winter heating fuel needs by more than half, compared with a comparable log cabin in the same Colorado Valley, whether or not any one miner ever enjoyed a constant 65 degree stacks without burning a single log. If you value practical, evidence-based frontier and homestead techniques, and want more work grounded in archives, measurements, and real performance, consider supporting the channel.